Huh, okay. That's odd. Yeah, the graphic one normally works pretty well. Are you on Windows or Mac? Oh, I can type it, I guess. Is it easier for me to type or just speak it? All right, Windows. I'm less familiar with that, but I think you can still launch it from the command line if you want to try doing that. Just on command prompt, you could type, I believe it's the same on Windows, just Jupyter Notebook, 2 separate words. Or Anaconda prompt. No, I think if you just open command line, command prompt, sorry, and type in Jupyter with a Y, notebook, 2 separate words, it should do a separate launcher. Like I could show on my Mac equivalent. I don't know if that would be helpful for you. Okay. Cool. Okay, so I had it open before, so I'm just closing it. Oh, mine's not working either. Okay. You literally just type that. For Mac, it would be in terminal, and Windows, it would be command prompt. And it should start the server and pull it open here. Yeah, you just start the server, and then the server, once it starts, it opens up here, and you can navigate to wherever it is. So mine is docs. Harvard, QCA. Awesome. All right. So let's see how we could do this. If you got it open and I've got it open, maybe we can just step through it and I'll just talk a little bit about it and then hopefully you can get it or something. Oh, awesome. Okay, you got it. That's a good idea. Cool. Okay. So if you go to the top, we can start working through it. Yeah. So I think you need to import first. And also a shortcut for inserting above. If you have it highlighted, you could just press A, which is kind of nice. Yeah, don't click in. Yeah, but see when it's blue, it's green right now. If you click, press escape, it'll turn blue. And now press A. Yeah, those are like shortcuts for adding cells. Yeah, that's perfect. Yeah, you got it. So now you imported it. And it's not, scroll up, you see, okay, I kind of rushed this a bit, sorry. So import Qiskit is Q, and then what you want to do, QC is actually creating a quantum circuit class. So yeah, I totally should have put this in the notebook. Yeah, so what you want to do is, I'll text you the code or whatever, send it. Okay, so QC is equal to quantum circuit. Yeah. And you need to Q dot quantum circuit because you imported Qiskit as Q. Also, if you want to delete a cell when it's blue, you can press DD, that deletes it. Nice. Okay, so yeah, maybe just change your import at the top. It's totally up to you how you import it, but to make it easier, you can import everything from Qiskit, and that way you don't need to type it Q dot whatever. Do you know what I'm talking about? And it looks like you made that cell markdown by accident, so it's not going to run. I don't know the shortcut. You can go to cell type up at the top and change it, or just do that one. Code. Cool. And then import Qiskit as Q. And then do Q dot quantum circuit. QC is equal to Q dot quantum circuit. Because quantum circuit's from Qiskit. Just Q dot in front of it. Yeah. Perfect. Yep, and that's exactly what you'd expect. So that's instantiating a X gate in the Qiskit quantum circuit. But I suggest just leaving it. Yeah, it's already in there. All right. So if you scroll down, we could just start the lab things. It's not like crucial that you know exactly. I think right now we want to focus on the Q-tip first before we go to Qiskit, because if you get Q-tip, the Qiskit's way easy. Yeah, I mean that's all it does. And you can see it flips the basis state. So everyone's seen the 0 state and the 1 state. So sigma x is, if you scroll up, you can see, yeah, so scroll up and stop. See the X gate? I introduced it right there under single qubit gates. So you says single qubit gate, the X gate. And it says, yeah, right here. So sigma x is how Q-tip describes that X gate. It's a function that produces that 2x2 matrix. Yeah, it's like a bit flip. It flips it. So where like a classical NOT gate could be represented as a sigma x. Obviously, it's different because it's doing, yeah, exactly. It's different because it's a quantum 0 state to a quantum 1 state, which is not the same as a just like a, and you know, run of the mill NOT gate. And you can see it on the block sphere below, with the green, the red, and the orange. So green is the vector at first. That's the 1, 0 vec. And then it flips it after the X gate's applied. Yeah, it's bit flip. Okay, so what you did there is totally the right idea, but you can't actually do that. So the basis function just initiates the vector, and you have to initiate it. And the numbers you give are referring to what part of the column vector you're pointing at. So if you have basis, I believe it had 0, 2 there, or 2, 0. 2, 0, yeah. So 2 is saying you want a 2 side, like a dimension 2 vector. And then the other one refers to what part of the vector you're pointing at. So the 0 would be the bottom. So let me give you a bit of a hint here, because it's totally not obvious just based on what you've done. A basis 2, 0, and you could write basis 2, 0, and you could write basis 2, 1, and you can create a Q object out of the two of those. Did I write the Q object function in here yet? No, that was totally my bad. Okay. So write basis 2, 1 and see what happens. It's the equivalent of having the arrow in the other direction. Yeah, you totally got it. Python uses complex numbers. It uses J instead of I. But you were totally on the right track. And if you wrap it in a Q object overall, it should be able to figure out what you mean by it. Yeah, I didn't write that class. Check the thing I just sent through to the chat. That was my bad. I thought last week Tommy went over Q objects. Cool. I think you don't need to multiply the 0.975 by J. It's like a weird, it's a weird Q-tip thing. Just put 0 point whatever directly next to the J. Oh. Yeah, that's weird. I don't know what 0 point's about. So just replace that. You see you have -1J there. If you replace that with the multiplier, then 0.9755 without an asterisk between it, that should give you the correct. And now you want to multiply your basis. Yeah, multiply your basis by 0.2, that one. Cool. And now just plot that on the block sphere. So if you create a new state, just make it equal to that Q object, and then you copy that block sphere code, and you should be good. Yeah, you need all 3 lines. Yeah, exactly. Yep, and maybe just plot the initial state too, so you can see. Sorry, just do the same thing and then apply the sigma x to it. That's my bad. So do your practice state and then apply sigma x to it, and then plot that too. And make sure it's part of the list as well. So yeah, you see a practice state in the. Yeah, so you have practice state in the list. You want to make a comma after that and add your next state to that state list. Yeah, no, don't make another list entry. It's not a tuple. It's all in that list. So do b dot add states, and then you open the parentheses, start the square brackets, practice state, comma, flip state. You know what I mean? Yep. There you go. That's correct. So you see now how it's not necessarily a bit flip, it's more a vector flip. Yeah, exactly. And that's what makes it so cool. Doesn't matter what your like multipliers are, your alpha and beta. It'll just flip what alpha is multiplying each time. Yeah, exactly. Cool. Okay. So these next two gates are super important. I had them on an RFI. I don't know if you came across those last time. Yeah, you could just run the markdown block and to get it back to how it was. Shift enter. Yeah, there you go. So maybe a good exercise here would be to plot on the block sphere again the basis state with a Hadamard applied to it. Yeah, so that's what you had before. See if you could just initialize a basis state and then apply a Hadamard to that. And to create the base state, it's basis 2, 0. So that, yeah, remember you need to add your states later. You're still showing the previous one. And we want to apply a Hadamard here as opposed to a sigma x. Hadamard is S naught. See, it's right above there in the Hadamard section. Yep. Yeah, it looks like you've got some other vectors in there because you added them in the same cell. So you might want to create a new, redefine B to be a fresh block sphere. So do B equal to block. It's capital B. There you go. That bottom one's correct. The top one's showing the previous one. So see how it flips it from the 0 state onto the XY plane? It's now in a superposition between 0 and 1. Oh, my bad. I forgot to unmute myself. Okay. So do you have an idea of what to do here for creating the Hadamard? Sorry, I think it's the X gate. What'd you say? Okay, you did Hadamard multiplied by Rx of 5. So you need to give 5 a value in radians. So probably just functional programming. No, it's not. It's not functional programming. Give 5 value. So like do, and it's in radians. I think numpy was imported at the top, so you should be able to do np.py. What's the error there? At the bottom of that block. Oh yeah, so the S naught needs to be, instead of that 0, make it 1. So it's acting on the first qubit, because it's a 2 qubit gate. And on the np.py, comma 1 as well. All right, let me check my results too. Give me a minute. So it should be able to work with Hadamard, and then you want to do it, essentially simulate a Z gate, and then Hadamard again, and that's the equivalent of an X gate. Yeah, it's Hadamard, then Z, and then Hadamard. And is your practice state a basis state? I can't remember how you defined it. Okay, yeah, yeah. Just do it to a basis. It makes it easier. Yep. Okay, well, that is correct, regardless of it giving a depreciation warning. And in terms of drawing that on a block sphere, do you understand why applying the Hadamard twice is able to essentially alter the direction of a Z gate so that it's in the x-axis? Yeah, pretty much. It's an important concept when we cover it. We'll do phase kickback next time, and that will make it a lot more clear what's going on with phase kickback. I mean, I wouldn't make a note of it. Yeah, it's going to be next time. It's a pretty hard topic, which I figured we had enough to cover today. Cool. All right, I think you're good. Now we're on to the fun stuff. Oh, I forgot to add in. Is there the question there? Yeah. Okay. This is a trickier question. Do you have any idea how to start this one? Okay, that's Yeah, you definitely want to keep them at 2, 0 because that initializes the right size column vector. Okay, so now you've tensored both of them together and you have a column vector of 1 and 3 zeros. So that's equivalent to the 0, 0 state, 2 qubits in the 0 state. And what we want to have is a superposition of the 0, 1 state and the 1, 0 state. So you definitely want to have a Hadamard in there at some point. Okay, so you have a good idea there. You tried multiplying one of the basis states. Try and keep that whole 0, 0 basis state all together to begin with. So that's one thing, and you're trying to pass that through gates to get the result you want. Nice. Okay. And think how you want your column vector to look at the end. You want the 0, 1 state and the 1, 0 state to have 1/√2. And you don't need to use the RX gate, but you will need to use a controlled gate, a C naught. So try applying a just a Hadamard to the tensor. Should be inconsistent size. Yeah. So see, if you stop for a second, so right now it's giving you an error because it's incompatible object shape, which means that you're trying to do a 2x2 by a 4x4 or a 4x1. And what you need to do is make that S naught apply only to a single qubit, but make it a 4x4 matrix. And I'd say the hint here is to use the identity matrix and the tensor. So you see when before I did tensor and then parentheses and I gave it two 2x2s and that returns the tensor of those 2x2 or that 2x1, sorry. This is pretty tricky, by the way. This is very tricky. And I did not give you much to work with, but yep. So you don't want to do a tensor with the whole thing. Yeah, not quite. Keep that basis. You definitely need to start with that tensor basis 2 0 basis 2 0. That's your starting states. You can't really change that. Yeah. Okay. And now what you want to do is make a new gate. So you could just call it like, I don't know, NG is equal to, and then you're going to do tensor of S naught and identity. And here's a hint for the identity matrix. Yeah, that should return a two-dimensional identity matrix. So try tensoring the S naught and QI together. Nice. Okay, and now try multiplying that by the basis state, the 2 qubit basis state you have above. All right, so that's pretty close to exactly what we want. See what happens if you put the QI2 first before the S naught. And you can see how that changes the ending state. And then you're almost there. So now you've applied that to the top two. And the difference is applying that either to the A qubit or the B qubit. If you look at above, that's essentially what's happening. So your Hadamard is being applied to only one of them. If you look in the example below where your mouse is, yeah, in that one, see it's like being applied to just one of those. That's why the 0707 is only in one of those spots. Okay, and then the next bit you need to use is a controlled NOT, a C NOT gate. And then parentheses. Yeah, so you don't want to be tensering it. The C NOT's already a 4x4. So it's just a straight multiplication. Okay. 0, 1, and 1 state have 1 over square root. That's rotation around 45 degrees. Yep. Okay, so I will have to close the office hours kind of soon, but you're super close. I don't actually, I can't actually run it on mine as well at the same time, but it's essentially just a combination of exactly what you're doing. Um, I want to say you'll get it. I think you'll get it. What do you think? All right, bye. Thanks for coming.